Okay. Let's see here. All right, so welcome everybody. This is the Robotics Society of Southern California's monthly meeting. Welcome. I am Ben Partida, the current president, along with Jim DiNunzio, our current vice president, and all of other members. Welcome. Today we have a special guest speaker, Kevin. Sorry if I mispronounce your name, Knoedler. He is one of the DARPA Challenge participants. Jim, maybe you can give a better introduction to Kevin.
Yeah, Kevin has been a member of the Northern Cal Robotics Society for a few years, and so I found out about him through there. But the homebrew, and he has quite a history. I read an article in Wired magazine not that long ago, which outlined his achievements in the DARPA challenges. And I wrote a little bio that if it didn't get published out to you guys, I'll send it out later. But he's been very instrumental for many years, working from the beginning of the DARPA challenges, and taking first place as a solo contender in the virtual competitions multiple times. And then he has a team in the University of Cal Cal State, the islands and Channel Islands, and it's a very meager funded group, and of undergrads and even younger students, and they have achieved quite a lot compared with the extremely well-funded universities and organizations. So he's going to talk about his experiences working on these DARPA challenges, and he's quite a hero to most of us in robotics, because he's done all this it is a hobby, though he's won 6-figure prizes in multiple situations or multiple contests. But he's a stay-at-home dad, and he's been able to achieve all this through mostly self-taught. So, but he did go to MIT and work for Teradyne. So without further ado, Kevin, take it away.
Good morning. So I'm going to go over I'm going to talk about the SubTerranian challenge primarily. I'm going to go over what the contest is, talk about the simulation side of it, have a break for questions. You don't have to hold them all to the end. Talk about the systems track, the physical robots and the contest, and then have another section for questions. If you have further interest, always feel free to contact me, and there are thousands of hours and hundreds of papers about the contest on the web for more information. Let me start our little slideshow here. Okay, so how is that showing up right now?
You still see the slides.
Yeah, so we can see the slide with your thumbnails on the left-hand side.
Okay, so that's not quite what I wanted. Let me change it again then.
I think you might be sharing just the.
Yeah, I'm just sharing. There we go. I'm just sharing the one, not the one I wanted to share.
Yeah, you need to share your screen.
There we go. That should work better.
There we go.
Okay, so like I said, go over the contest, go over the virtual portion of it, simulation, and ask questions, and then the physical, and then more questions. So the DARPA SubTerranian Robotics Challenge is also called the DARPA SubT. There's two portions to it: the virtual track, which is all simulated, and the vehicles must be fully autonomous. There's no interaction with the people. You basically submit a Docker image, and it runs that Docker image against the various worlds that are in the simulation. And that's how that is. The systems track is real vehicles, real robots. There's one operator allowed, and then there is a pit crew where the people can prepare the robots and fix anything that happens to be broken. Those robots then have to go into the underground situations and find whatever is there. The teams could compete in either one or both of the tracks. There were 4 rounds in the competition, and then there was sort of a test situation at the Colorado School of Mines has a mine that they did some initial experimentation at. And then there was the actual competition at the tunnel, which was at a coal mine, the urban circuit, which was a partially completed nuclear plant, the cave circuit, which was only virtual due to COVID, and then the finals were at a limestone mine in Kentucky. Some of the teams were funded and some of them were not. We were not a funded team. The funded teams could only win prizes in the final round. They weren't eligible for prizes in the earlier rounds. The overall goals of the contest were to report locations of artifacts back to a base station outside of the underground scenario with less than a 5-meter error. Correctly identify the various artifacts with little or no ambient light. They had a variety of different artifacts you had to find: survivor, cell phones, backpacks, drills, fire extinguisher. CO2 was an interesting one as a gas. You had to detect it. You had to keep track of the robot location and artifact locations without GPS. And the robots had to work together. So you had to have some way of coordinating what each robot was doing. Being able to communicate in an underground environment, and then being able to move around in an underground environment with rocks, mud, various obstacles and such. The contest itself, they typically had 20 to 40 artifacts in each round and a 1-hour time limit. Let me go ahead and share a little video from DARPA here. They have got several of these we'll show.
You're not sharing audio if there is any.
No audio, huh? Let me see if I can figure out how
that's
to
okay.
share the audio.
That's always a pain.
You might have to click that button, share audio, when you first share the screen.
Let's try again.
Run into that a lot where I work with YouTube, not able to share audio.
There we go, share sound. Thank you for letting me know. Okay, so that was actually the urban circuit, just to give you an idea of what the underground environment was like for that one. Go back over to here. Okay, so the virtual contest took place in the Ignition Gazebo Simulator. put out by the OSRF group, same group that does ROS and a number of other projects. The environments will generally model to be similar to the systems track. So they try and model real scenarios in there. They tried to model the same robots in the systems track were also available on the virtual track. And they had a variety of scenarios to test against. For the competition rounds, you basically submitted a Docker image, which was a self-encapsulated image of all your code and how it was supposed to run. And they just ran that directly against the worlds. And so that's how the tests were done. It was, again, I mentioned fully autonomous. There was no interaction with from me. I just basically submitted it and then found out later how that scored against the various worlds. So when I was debugging it, I would typically watch it and see what was going on. And so this particular is a screen capture of what it looked like after it mapped out a portion of a world. The red lines are where the robot had traveled. The white dots, I used a graph-based approach, are the nodes for each graph. The green dots are paths that have been explored from that node, and the red dots are paths that remain to be explored. So near the top, you can see that it has a red dot looking to explore that path out over there. But over on the left, you'll notice that there is a path that did not get properly mapped out as the robot was passing through there. So it missed that particular spot. And so there was always infinitely more work to be done. I'm sure you're all familiar with that. But you can see that how the overall graph-based approach worked. It used my particular approach. I used a couple of ground vehicles and a number of drones that would use either depth cameras or LiDAR to keep track of their location as they were traveling. Okay. Problems are always interesting. So as I mentioned, there are different circuits for it. The first circuit was the tunnel circuit. And so there were challenges with the simulation software. So for example, I had focused on using only UAVs, and it turned out the UAVs did not work in the simulator for the first round. And so a couple weeks before the end of the contest, I had to switch over to ground vehicles. So that was a challenge. The simulation runs, the simulator ran at between 1/4 and 1/8 of real time for the first round. So for a 1-hour contest, you're typically looking at 8 hours of real time to test it on your computer or in the cloud. I used graph-based planning to do the overall coordination of the search between the robots. Locally, I used A-star using the LiDAR and depth camera data for local navigation, so it didn't run over edges or into walls or get stuck on rocks and such. I used Luminoth to identify objects. Luminoth was really helpful in that it could run either on the GPU or CPU. And so if I was running on a system with only CPU, I was still able to do simulation, get everything to work, and before running it on a system with a GPU. Mentioned the LiDAR and depth camera based localization. So those are the problems I ran into the tunnel circuit. Urban circuit, there were more vehicles. They had the simulator working better. And so now rather than 48 hours, it could take 8 to 12 hours to run a simulation. And so I started running on 2 simulation computers for the urban circuit, but those are the main problems I remember there. Cave circuit, the new NVIDIA GPUs came out. And even with the scalpers, I was able to get one on eBay. But then I found out that I could not get Luminoth to work with the new GPU. So it was fun to have it, but it wasn't useful at the time. And then for the virtual contest for the finals, I tried bringing in a contracting company. I don't know how many of you have worked with contractors before. I've worked with them before in the past through Teradyne and other situations. And it ended up being a bigger challenge trying to coordinate the contracting company. Ran into lots of schedule and communication issues with them. And so ended up not being able to use the work that they developed. Another issue I ran into in the finals was getting the ground and aerial vehicles working together at a high level. Took more time than was available. Not really an issue, but I switched to a YOLO v4 from Luminoth. Probably more of you familiar with YOLO rather than Luminoth for my object recognition. As a bonus, my GPU worked as well then. And in the finals, the runs could take 24 or even 48 hours locally or in the cloud. So I added some more simulation computers that were just running simulations constantly to be able to test and see how things were going. So now another video.
The DARPA SubTerranian Challenge virtual competition pushes the limits of autonomy by challenging simulated robots to explore virtual underground worlds. To win, competitors must build software to drive or fly simulated robots through the virtual worlds, gaining points by locating hidden artifacts that represent items that first responders or service members could encounter underground. The worlds are designed with obstacles, constrained passages, vertical elements, and degraded communications. The worlds mimic real tunnels, urban infrastructures, and natural cave networks. Tiles can be used to build new environments. The scale and diversity are limited only by your creativity. The robot teams must navigate through these challenging environments completely autonomously with no human interaction. Competitors build their robot teams by choosing from the platforms and sensors on the SubT Tech repo. They can build teams of multiple robots, though they must choose wisely. Each item has a value in SubT credits, and competitors only have 1,000 SubT credits available to build their teams. Virtual competitors then add software to each of their robots to autonomously map, navigate, and search for artifacts in the simulated environment. That's how teams take on the SubT Challenge virtual competition and revolutionize how we operate in the underground domain. Are you up for the challenge? Get your team ready.
Okay, so I just want to point out one thing in there. If you saw the vent that they had, that was one of the artifacts we had to find. That was one of the harder ones to find because it was just various shades of white. And so it was very challenging to train the neural networks to be able to recognize vents compared to other things that had more color and more interesting patterns on them. That was my section for the virtual challenge and the overall contest. So we'll have a break for questions right now. Any questions at the moment?
I do.
Go ahead.
Can I pick up this software? And I assume the contest is over. Can I pick up this stuff and start playing with it still?
Yes, the software is still available. It runs on Ubuntu 18. And let me see if I can find the link to that. I'll just share it real quick.
Also, how hard is it to get all this going?
I'd say medium hard right now. Gazebo used to be very difficult, but they've made it more user-friendly in terms of getting it up and running.
Oh, and that was going to be my first question. Kevin, what was the simulation environment? You said that was Gazebo?
Yeah, that's correct.
Wow. Okay.
Was this on ROS, regular ROS 1?
This was ROS 1 versus ROS 2. That's correct.
Yeah.
And generally, what does your software have to do? Is it writing a behavior tree, calling an API?
So the software had to keep track of where the robots were, identify the objects, deal with degraded communications, and coordinate among the robots and navigate. So it's a fairly large software package in terms of everything it had to do. It used a lot of lower level packages to make that happen. So there is the software. The key page for getting started is here. So can everyone see that link then? The OSRF SubT get started?
Yes. So Kevin, you said the robots have to track or keep track of where they're at in the simulation. Are you assuming you're using some kind of odometry, or how do they keep track without any kind of GPS, or I don't know, what was the mechanism inside there that you guys used to keep track of where you're at?
So there are a number of different approaches, but like one of them I'll talk about, it's called LeoSam. It's a simultaneous mapping and localization, so SLAM type package. That particular one used the LiDAR, the simulated or the real LiDAR. And each time a LiDAR spin was completed, it would take that and compare it to the previous one and then relocalize the robot based on that data.
So it was SLAM.
Correct.
So that's a 3D mapping?
Yes. The Velodyne LiDARs that we use primarily had about a 30-degree field of view. And so if things were good, they could keep track of their Z fairly accurately, but with the narrow field of view, it was harder for them to keep track of their Z location accurately. We also used a couple of Ouster LiDARs that had a 90-degree field of view, and they worked better for keeping track of their Z location with that wider field of view, because it didn't take very much for the robot to tilt more than 30 degrees in a short period of time, and then it would lose track of where it was.
So Z, in this case, Z is up, down, or?
Correct.
Yeah. And right, the caves and all that altitude changed all over the place, I assume.
In the simulation more so than in the real, but yeah, there was definitely some change in Z.
So these are a lot of sensors and processing. What kind of compute hardware was on the bot?
We used let's see, they're like the Intel nukes, but they were the gigabyte bricks version of that. And so it was a quad core Intel CPU. Typically we would run with 32 gigabytes of RAM and an SSD to log data. That's what we used on some of the smaller robots. On some of the larger robots, we used laptops. We also had a GPU available. The GPU really helped speed up the image recognition, and some of the algorithms we were running were also able to use the GPU. Then the last one we used is the Xavier NX from NVIDIA. It's basically a small ARM and a relatively beefy GPU on a small board. And that was the main processing we used. We had a few various microcontrollers for running some small sensors and things like that, but that was where most of the processing was done.
Gotcha. You mentioned that you're able to integrate a GPU in some of the bots. What type of GPU were you able to get on the bot?
Only NVIDIA GPUs. Like the laptops had them, and so did the Xavier NX boards.
Gotcha. Okay.
Who else was on your team? What did your team look like, and how did you coordinate all of this work?
So for the virtual contest, it was just me. I tried bringing on the contractors, but had some trouble there. For the systems contest, I'll go over that more when I talk in the next section. I have a lot more pictures of the robots and the team and more videos and such there. Any other questions about the contest or the virtual portion of it? And then I'll go on to the system portion.
So in with the ROS, using ROS and the existing like I assume use the cartographer and the various nav system, or the nav1, right? I guess it is.
I wrote my own navigation and did not use cartographer. I used the LeoSam and other packages in place of cartographer.
Okay, so it was custom. And was it ACE? Did you kind of use an A star, or like for path finding? I assume you yeah, you see you set a point where you, and then try to follow up, create a path. So you had to do some path finding.
Yeah, I use some A*. There's also a package, you see, what's that map called? Octomap. It's basically a 3D grid cell type system. So I use that for building 3D maps, and then I wrote a custom planner to plan that. A* worked well for the ground robots, basically on a height map, but it did not work as well for aerial vehicles in a 3D space.
Oh, right. So you had your own custom planner for that. You didn't use any like aerial, you didn't use any off-the-shelf software like we have.
I really wanted to, and so I tried, but I was not able to successfully get those working to the degree I needed to.
Okay. Thank you. It's a lot of custom work.
That's really what it takes for a lot of these things. Sometimes you can reuse packages like LeoSam, one I've mentioned several times here, was something someone else wrote that I was able to use. And so that's huge time savings. That's a SLAM package is beyond what I can write. I can do navigation and some other stuff, but the SLAM is something I have to use off the shelf, regardless of how much I want to right now.
And the inputs to the SLAM was were LiDAR and
IMU is the other key one.
IMU and LiDAR. No, odometry of any kind as well.
We did have odometry both on the real and the simulated robots, but both cases, as soon as you have any wheel slip, you start running into trouble pretty quickly.
Yeah.
And
Go ahead.
Sorry. In the simulation environment, were you simulating these communication problems?
Yes. They also simulated communication problems, and droppable nodes for communication were also simulated. And so the simulation, they basically simulated it. It wasn't not perfect, but they basically simulated it such that it wouldn't go around corners and that it had a limited range. And so it's not a perfect simulation of the underground environment, but it's pretty reasonable.
And we're using ROS for communication between the robots, or was it something else?
There was no communication at that high level between the robots. You had maybe tens of kilobits or less between the robots, depending on where they were. And so ROS, you had to use something custom. ROS is not very good at low bandwidth communication.
Nice.
Okay, I'll start my screen share back up for the next segment. Okay, the systems track. There was a earlier one at the research mine that we didn't go to. I went to the tunnel circuit on my own before I got CSUCI involved. I took 2 suitcases and disassembled about 10 drones and carried them along in 2 suitcases and then reassembled them there. That turned out not to be a very good choice, as the reassembling drones takes a lot of hours, and there were not that many hours in the day to get all the drones reassembled. And then I had lots of fun crashing them there. There are lots of issues I ran into. I'll talk about that some more. I got CSUCI to come to the urban circuit. We had a very successful run at the partially completed nuclear reactor up in Washington at SATSOP. The cave circuit ended up being canceled due to COVID. I was really looking forward to that because I enjoy caving, actually took some cave rescue courses and enjoy robotics, so it was a nice combination. And then the finals were in Kentucky, which was a limestone mine modified to have sections like a mine, subway, and cave. So we had a whole bunch of robots. We had some on the left there. You can see it's a skid steer robot. It was a security robot we bought off Craigslist, bought a couple of those. You have the bicycle robot right there in front that we had one of the students built. We had some 4-wheel robots in the back that we built, and then some other robots and drones that aren't visible in that picture. When we went to the finals, we took 15 ground vehicles, 8 drones, and about 3,400 pounds shipment that we shipped via truck to the contest. Here's a picture of the team. Professor Isaacs, who's the robotics professor at CSUCI, is there on the right. He's teaching there, and so he's a good person to contact. And then we have a lot of primarily undergraduates in the picture there. There is one graduate student. A couple of those students, one in the center. Hugo's moved on, is working, I think, over at the base now. And Andrews took a graduate position up at UCSB, so that should be good for him in control theory. Bottom left, I also run a robotic club over at the middle school. And so they helped assemble one of the four-wheel robots that was based on some hoverboard wheels. You can see down there. Our overall strategy of the contest for communications, rather than using only wireless and dealing with those issues, we plan to run fiber optics into the underground environment and then use a wireless mesh to extend that. In the narrow areas, we plan to use wall following or manual driving and then switch to a frontier exploration in the open areas. We had wheeled vehicles for the flatter areas, treaded vehicles for stairs and rougher areas, and then aerial vehicles for vertical areas or wherever we'd want to. That was our goal. Okay, and then I guess we have some finals issues here, but why don't I show a video before then? That was.
After 3 years of development in circuit competitions, roboticists, engineers, and technologists from 11 countries participated in the September 2021 final event of the DARPA SubTerranian or SubT Challenge at the Louisville, Kentucky Mega Cavern. The teams innovated novel approaches to rapidly map, navigate, and search underground environments during time-sensitive combat operations or disaster response scenarios. The SubT Challenge held 3 previous events: tunnel, urban, and cave circuits, where teams competed in those specific underground environments. The final event brought all 3 domains together in a DARPA-built course designed to maximally test robots' abilities. 8 systems competition teams deployed their physical robots on the course in search of artifacts, ranging from mannequins representing survivors, to lost cell phones, to noxious gas. In the virtual competition, 9 teams submitted software solutions that SubT Challenge officials then tested across 8 courses, one of which was the virtual model of the DARPA-built course at Louisville Mega Cavern. The systems competition winners were Cerberus, Cyro Data 61, and Marble, winning $2 million, $1 million, and $500,000 respectively. The virtual competition winners were Dynamo, CTU Krasnorlab, and Coordinated Robotics. They took home prizes of $750,000, $500,000, and $250,000 respectively. With the final event concluded, now the goal will be to ensure that our warfighters and first responders are equipped with the new technologies and capabilities generated by the SubT Challenge competition, helping them more effectively execute future missions. For additional information on the DARPA SubTerranian Challenge, please visit subtchallenge.com.
Okay, so talk about some of the issues you ran into, and then I'll go over some more details about how our robots worked and some of the robots. So we all had the COVID challenge. So the contest was in September 2021, the finals. We didn't have access to CSUCI until July 2021. And so we had no in-person meetings and no access to the campus until a couple months before the contest. That put a crimp on things. We ended up having some of our robots shipped to students' houses. And so we had students running some of these robots at their houses. It's a little bit scary having big robots out in the wild undergraduate student houses, but it worked out. We had some hardware failure shortly before they shipped. Those things happen. I mentioned we shipped the robots. We shipped them early. So they're supposed to arrive a couple days before we got there. And you've read about all the shipping delays, and this was even planning for shipping delays. They were meant to arrive. We got there on the 16th, and the robots, they told us they'd be there on the 15th and the 16th and the 17th. And they actually physically, we could track and see where they were. And they were finally in Kentucky, and actually they were in Tennessee when the first time we saw them. We said, we'll go pick them up, but then they couldn't tell us where they were anymore. And so they were finally in Kentucky. And so we just had to keep harassing them so we could actually go physically pick them up. They were going to hold them for a few more days because they were busy with other things. And so that was a frustrating one right at the end there. During the actual runs, the first practice run, we had a number of robots that wouldn't start. Our second practice run, we used automatic alignment. There were April tags on the entryway, and we used those for the robots to figure out where they were and to localize. And that software was causing software crashes on the robot to start. And then the final run, when the robots were actually inside, the narrower passages were what caused our localization solutions to fail. And so that was a little bit of a surprise, but it was frustrating because that sort of put a crimp on what we could do. So then going over how our robots worked, how they moved. We had some ground vehicles. We had the hoverboard robot type ones on the left, and then some bigger four-wheel skid steer robots on the right. So you can see each of them have lights at the top. We used a fisheye camera. It's the USB type one. You can see just underneath the lights there by the yellow tie wraps, and then a depth camera, one of the Intel depth cameras facing down. The silver camera with the black spot in front on the second page below the Velodyne LiDAR. And then the Velodyne LiDAR right there. Other sensors, we had CO2 sensors and IMUs and things like that. The one on the left, labeled 14, had like I mentioned, a gigabyte bricks, Intel quad core inside. The one on the right had a laptop inside of it, so it had a bit more powerful processing and a GPU. Then we had some tracked robots. There's a company that sells those as a kit, and so we assembled them. Similar set of sensors. I guess another thing I didn't mention, you can see the Wi-Fi tie wrapped on there. Wi-Fi got damaged a bit. Whenever the robots got tumbled over, the Wi-Fi would be the first thing to get squished, but luckily, it's not too expensive to replace. Those used either gigabyte bricks or the NVIDIA Xavier boards. Then on the right, we had the ones that had that were the security robots we bought off Craigslist. Again, a similar set of sensors. Those ones also had ultrasonic, you could see on the front. There are some portions of the course where they used fog to mean you couldn't see anything. And so that impacted both the LiDAR and the camera. And so the goal was to be able to use the ultrasound to be able to get through those sections. We have the bicycle robot. It had a center pivot, so it could keep all four wheels in the ground. Used 4 e-bike motors on it for mobility. Then we had a rock crawler, RC rock crawler vehicle on the right. It wasn't big enough to put a LiDAR on it, and so it used the depth camera. Had a fisheye camera front and back, little LED lights for that. And then we had our collection of drones. We had one drone that actually 2 drones we had LiDAR on. One of them failed shortly beforehand, and the other one we ended up not flying, but we did have some with LiDAR at the end. We didn't fully get those debugged and working to the point we wanted to, though. They were mounted on top of some of the larger ground vehicles, so the ground vehicles could drive them in as far as possible, and then they could take off. I'll mention it later, but one of the big challenges we had, it turns out that the computers, the Wi-Fi modules on those computers were not compatible with the mesh networking we were using. And so we were not able to get the drones on the same mesh network as the other vehicles. And so that caused, we could only really use those near the entrance is what ended up happening. Let's see, mobility, a couple of videos here. The tank track vehicles could go upstairs, go over rough things relatively easily. No big issues there. Some issues with localization. You can see how it tilts fairly quickly and bounces over. That caused some issues with keeping track of where it was. The one on the next video then is on the bottom. Apparently this goes up the stairs fairly well, but then we tried going down the stairs after the contest just to see how well it worked. And you can see the person there behind driving it just for testing purposes. Always challenges. It still drove after that. So the wheel was bent and so it wobbled a bit, but still functional. So that was a good sign. Okay, communications. All the robots had to send reports back to the base station. And so you could either have the robot go out on its own and come back, or you could have it be able to talk to the base station as much as possible. And so we wanted to be able to have the robots talking to the base station all the way. We added a mesh networking program package onto it. For the urban contest, we used a manual routing. We actually had a manual routing table we'd pull up and tell, okay, robot A talk through robot B through robot C back to the base station. And base station talked to robot A through C and B. And so that was functional, but very slow and error prone for the operator to try and manually route everything. The robots would automatically detect when they found things, their positions. So we had a little map showing where things were. And then we had enough bandwidth to have video from one robot while we were operating the robots on the contest. Basically, we were aiming for our mesh network to have a megabit per second of throughput and roughly 100 packets per second total throughput for the mesh network in the system. And so that was our mesh networking goal. We had the gigabit fiber that would roll out behind the vehicles. And then we had 802.11n on each of the robots for talking. We also had droppable nodes that the robots could drive in and drop that had 802.11n repeaters on them. Of course, there were issues. And so those are always one of the more interesting things to me. Our first attempt at the droppable nodes, we used a section of PVC pipe with a Pi0W inside. And so it basically, you could have a batch of those and you could roll out, have 8 or 16 of them per robot that would just roll out the back of the robot whenever it wanted to as it was driving along. It turned out that they worked pretty well inside or if you're on flat ground. But if you got on even somewhat rough terrain, the nodes would roll into the little dips, and then the signal propagation path would be completely blocked off. And so they failed pretty quickly. So we switched over to a Weeble Wobble type design. You can see there, it had a weight in the bottom and we put the Pi0W up on top. We couldn't carry as many of them, but then they were not as subject to even small dips. As long as the dips were not too big, those worked pretty well. One of the biggest issues we had with our mesh network was network flooding. If any one sender tried using more than the available bandwidth, the network would overload and it could shut down for tens of seconds. Wi-Fi has a hardware resend, and we couldn't figure out a way to get around that. So it keeps resending packets, and so you get frequent network flooding. And so we had to have both the senders and receivers automatically adjust their bandwidth not to overwhelm the network. The system we use is called Batman Advanced. It's a mesh networking system. It sends lots of packets between the nodes to monitor the links. And those packets, you start running into number of packet limitations on your network. And so we were able to reduce that, but didn't fully resolve that. And then the final issue we had with our wireless mesh was that the routing would frequently choose an unexpected path. And so if you could go from node 1 to node 3 to node 3, from node 1 to 2 to 3 with a nice 2 hops, and so you had a good path from 1 to 2 and 2 to 3, the mesh network would frequently use a marginal path from 1 to 3, even with the hop cost, the calculated cost per hop set to 0. And so we haven't figured that out. It's one of our things that's on the, we'd like to work on that some more and fully resolve that, because it'd be nice to have a good wireless mesh system that we could use for other robots. Other issues, we had motor controllers on the fiber reels so that the fiber could reel out as we drove along. We had motor control problems there. And so we fell back to unpowered reels. The fiber was strong enough, so that worked out fine. We did get the fiber with the unpowered reels. We got fiber wrapped around the wheel a couple times. And I mentioned earlier, we're not able to get the Batman Advanced running on the aerial vehicles with their particular Wi-Fi cards. We were able to deploy fiber. We were able to deploy the droppable nodes. We were able to extend our range into the underground environment using the mesh network, but there's still more work to be done for communications. Object detection. We used a couple of sensors that were either we had a USB interface or a MIPI interface, depending on the computer. We had them with the same lens and the same underlying sensor. They had a wide field of view, so we could see a lot of things at the same time. And then we trained 3 different recognition networks with the same training set. We used YOLO v4 on the laptops with the GPU, and that could run, I think it was fast. It was like, you could run up to 30 frames a second of recognition, which was much more than we needed on the laptops with the GPUs. Similarly, a different version of YOLO on the Jetson Xavier boards. It was also pretty fast. It was like 15 frames a second, which was a couple times what we needed. And then on the robots with no GPU, we used a different version of the network. It was about 1 frame a second without the GPU, which was a little bit marginal because you could miss things at that rate. We trained the network with 8,300 training images. The undergraduates didn't really like labeling images, but all of us had to label a bunch of images to get to 8,300 images. Object detection, we had various issues. Like, here's an image of the subway area. You can see the vent up on the top left and one of our droppable sensor nodes on the bottom right there. So we had both false positives, false negatives. We could only run 1 fisheye with the USB camera. We ran into USB driver issues, so only allowed 1 fisheye camera. We also had CO2 threshold issues. The CO2 level in this particular environment was higher than we expected, so we needed to tweak our CO2 threshold level. And we could detect the Bluetooth artifacts, but it wasn't automatic. The robot wouldn't automatically find them and stop at them. So there was some work to be done there. Bottom right, you can see it identifies some piece of white material that's roughly shaped like a helmet, but it's not really a helmet, even with a fairly high probability there. And so after the contest, they let us into the area where they were testing. And so we were able to drive the robots around manually. And so we collected about 200,000 images. We downsampled that. And then we removed the stationary images. And then we ran that through our networks to see how well they did against if the robots explored perfectly, how well would our image recognition do? And so of the 24,000 images, about 4,000 of them contained artifacts. And so we found pictures of quite a few of the artifacts then. Our network could correctly identify about half of them, 37 out of the 85 on the YOLO v4, and 23 out of the 5 on the YOLO v4 Tiny that was running on the CPUs because it's not as extensive of a network. And so then we had a total of 2,000 detections out of the 24,000 images we collected, 1,300 false positives and 3,000 false negatives. YOLO v4 Tiny numbers were there. And so it was just interesting to be able to go back and run it. And so we had the operator could screen the false positives and false negatives. And so we didn't have huge issues there, but it was just interesting to see that even with a lot of training in a real environment, the image recognition is functional, but far from perfect.
Kevin, a quick question.
Yeah.
How did you get the original image training set? I mean, were you create those yourself at home and then try to hopefully match the real environment?
Yeah, so they told us what artifacts we had to look for. So we could train it against fire extinguishers and helmets and the dummy that they were using. And so we had relatively good initial data on what we were looking for. And so we'd use it at night with the cameras we're using, inside, outside, different environments to try and make sure we had a variety of training sets.
Thanks.
Okay, mapping. We tried to use similar sensor towers on each of the robots. We used the Velodyne LiDAR primarily, and then the Intel depth camera, and then a pretty good IMU. is what each of the robots had, along with lights and Wi-Fi. On this picture, you can also see a couple of other interesting things. You can see the USB cable leading up towards us, and there's just a little red board with an antenna sticking out right there. That's the wireless e-stops all the bigger robots had. So we had a wireless e-stop that was mandated by DARPA so that all of the robots could be stopped wirelessly. And on the back, let's see, I guess you can only see one of the buttons here. There's a red button you can press, big red button to press to stop the robots. And we also added another feature, which was you can see on the right side of the image there, you can see the red power switch. And so you could actually physically disconnect all power from the robot as well, in addition to the different e-stops. So that was a useful feature on the bigger robots if anything went wrong. For localization, I mentioned a number of things. We used LeoSam, which was used on the ground vehicles that had the good IMU and the LiDAR. Then we also used Lego Lone Boar, which was used on ground vehicles without a good IMU, because different algorithms have different requirements about how good of an IMU they require in order to function. Both those are LiDAR SLAM-based algorithms. And then we also used RTAB map, which is used with the depth cameras for keeping track of where it was. Okay, so here's a nice map of the CSU CI campus. You can see the trees and the buildings, and it actually works pretty well. We did closed loop testing to make sure we were within a meter over fair distances. And actually even indoors, we used some not super narrow, but relatively narrow corridors to try and test it out. But when we actually entered the course at the finals, at the urban circuit, it worked. And on our other test cases, it worked. But at the finals, the passages were more narrow than the algorithm could handle. And so our localization failed at the finals. We were able to do some testing further and make it better. So we ran the LiDARs through the course, and we modified some of the parameters for the LeoSam, and then we generated maps. And so here's the red map was generated with the Velodyne LiDAR. On the left side of the image, you can see there's the red area, and you can also see the blue path. Those should line up on the left image. On the right image, you can see the blue roughly lines up with the blue outline, and so that's a much better map. But that image, you can probably see there's a fairly large error there, and that would have been enough to throw it off at the far side of the map with the Velodyne, even with the tweak parameters. Autonomy. So we had the ability to drive the robots manually. They could also do wall following of a couple different wall following approaches. And then we had a deep reinforcement learning that would do exploration in open areas to try and it would drive around until it found an artifact. And then once it found an artifact, it would stop and submit it so that the human could check that the position and type of the artifact was correct based on where the robot was. Those depended on the localization working. And so during our final competition run, without localization working, those kind of broke down. So we ended up just being able to teleoperate. The learning was based again on a neural network. And so it took in the position history, the camera, and the laser scans to build up where it was, where it could go, and what it might try next. So here's a couple of it running out in some open areas. Basically, the robot would drive along and go exploring in a semi-random pattern until it would find one of the artifacts. Once it found an artifact, it would stop, report back to the operator, and then the operator could submit or deal with the artifact as necessary.
Yeah. How did you achieve the sort of random, sort of space filling or coverage type algorithm?
It was a semi off-the-shelf package we were able to use for that.
Oh.
It generated the packages. It would generate the paths based on what it could see there, and then keep on generating those images. It was always kind of fun to see the robots when they found an artifact or thought they found an artifact, stop and drive up to it.
once they saw something, it would kind of change, decide to go to it, I assume.
Correct. It would drive up to it within a few feet and stop. I don't remember if we captured that in the video, but this particular video is trying to show the semi-random pattern. With the 180-degree cameras, we could see probably 5 meters, see artifacts maybe 5 meters away. And so right now it's not really tuned real tight, so you don't have to go that tight into the corners, but it was very helpful to have the fisheye cameras for that particular purpose. And that is it for my slides. And so questions about the systems track or any other questions?
Back to your object identification, are you using just images like RGB, or are you using depth somehow as part of that?
For which part?
The artifact identification. So
We were using only RGB for the artifact identification. We had depth cameras. We were using those for navigation, for detecting obstacles, and drop-offs in particular. We didn't use that for artifact identification though.
Why did you choose a random search?
So the undergraduates worked on that. Let me try and think why they chose that. Probably because that's what that package did, and that was the package they got working. I think that was probably the extent of the reasoning there.
Okay.
Which is perfectly valid in my opinion, but that's.
I was going to ask about sensor fusion, and if you had to, for taking in the IMU and the LiDAR and with the SLAM, I don't know if the SLAM algorithm or SLAM algorithm, the SLAM code handled the sensor fusion, or if you did your own. Did you do your own on that, like with Kalman filtering and stuff?
So we did some Kalman filtering on the IMU because we had some of the robots had 3 IMUs, and so we'd filter those together to try and get a better output. And so we did some filtering there, but the package, the Leo SAM or the other SLAM package, did quite a bit of filtering for their localization. And so we didn't have to do a lot with that. We didn't have to add in GPS or anything like that. On the simulation side, some of the robots had both the depth camera localization and LiDAR localization. And so I did do some filtering of those because sometimes one would go out and the other wouldn't. And so you wanted to be able to have a good localization regardless.
Were you using a shared map, or does every robot have its own map representation?
Each robot has, so on the systems track, each robot had its own map. And so we direct them down corridors individually. In the virtual track, each one had its own local map, but they also shared an upper level graph-based map. So that was low enough bandwidth that it could be shared between the various robots. Because they had to coordinate between themselves autonomously without any human intervention. And so we couldn't have a human operator directing them down different paths or anything.
So was there a database then where you could for where, or the, I guess that's the mapping, huh? Each robot is generating its own map, or was it a shared? Well, I guess, yeah, each robot's exploring different areas, so that you had to kind of combine the explored, the mapping.
Yeah, so for the systems track, we pushed some of that map back to the operator, and so you could select which of the robots maps you wanted to see, or all of them at the same time. And so you could sort of, ideally it works out pretty nice, but with our localization not working, the meaningfulness of maps becomes quickly non-meaningful without good localization.
Right, because in the real world competition, it wasn't completely autonomous. Is that right?
Yeah, it was. You had one person that could see what the robots were seeing,
and issue commands. Sort of.
yeah, issue commands to the robots, tell them to go explore here or manually drive them.
Okay.
Were you able to share a lot between the simulated solution and the, I guess, the system solution?
I wanted to be able to have the same a shared software base. We did not get to that point. We were able to share the localization packages between the different environments. And so we had some, the IMU filtering and the localization using various packages. We were able to use the same packages. And we also were able to share our object detection. But the rest of the software, the communications and the autonomy, we were not able to share any of that between the two. We did not get to that point. Well, if you happen to have any other questions later, feel free to get in touch with me. And thanks for taking the time to listen.
Thank you.
So much for that. I guess as a final wrap-up question, with everything that you accomplished and worked with, would you do it again?
Yeah, I enjoy doing contests like that. And so you always learn a lot because when you actually have to do things and actually have to make them work, you are forced to learn, forced to solve problems or make your own solution.
Yeah, as a software person myself, I would just ask how much, how much time you had to spend and and how much you had to learn, or what you previously, or from what you previously knew about, all this, I guess, especially the part you did solo and the coding. I mean, there's some degree of taking in packages, that are available, but a lot of custom and a lot of integration. So yeah, how much effort was that percentage wise?
Well, time, it takes all of it. But so one of the big time consumers is, let's say you're trying to figure out how to solve localization, get localization working. So you look around and you find there's 20 different localization packages. And you've decided up front that you're not going to try and write your own localization package. And so you might first spend maybe 5 hours on each of those packages, trying to get them running, see how they work on a real robot, see how they work in the simulator. So you've blown off a few weeks just doing that. You narrow it down to the few that actually work reasonably well. And then you're spending another week or so. And so that's sort of localization. That's where the time went. It's just testing each of finding out, doing the research, reading the papers about which packages work, how they work, and then going in and hooking them up to the sensors, either on the simulator or the robot.
And then your custom code what percentage of it was custom, and time wise, how much?
The custom code takes less time up front to get working, but then you're spending more time on the back end debugging and improving it. I probably half custom, half. It's always hard to say exactly because, like the package you're using off the shelf, people have put many years of effort into those, and so that's a huge amount of effort you're not spending. So how do you count that time? It's obviously a huge amount of time avoided, but you generally have to do a fair chunk of custom code, because if it was possible to do most of these contests with off-the-shelf packages, then people would use off-the-shelf packages and they'd have a leg up. And so people tried doing that, and generally were not very successful doing that. It's just really hard to get a off-the-shelf package to work in a somewhat new environment. It's this not intended for. The three-dimensionality and the rough terrain really pushed most of the packages beyond what they are intended for.
Do you know if the SLAM software you were using was running on single precision or double precision floating point?
My guess is some of both, having looked at the code. Some of the bigger matrix multiplies, it used a mixture to try and maintain precision where it needed to and still be able to go fast. I'm not certain though, but you have all the links, you can go check. But no, that's my memory from what I remember seeing of it.
And the other question in my mind was, you had the depth sense camera, you had, I believe you said 3 different LiDARs. And the resolution, I know of 2 of those LiDARs are different. And I'm sure that the depth camera's resolution and depth is different from any of those. So how did did you have to do anything to integrate that, or did the SLAM software you were using, did that manage it?
So we'd usually we'd run one sensor with one SLAM package. And so there wasn't a lot that they didn't have to integrate across different sensors. I did some work to try and get the SLAM package to run with both the depth sensor and the LiDAR at the same time. And you could remap the sensors so that it worked out like that, but it didn't improve it enough to make it worthwhile to keep that software in place. Yeah, when we're using it for obstacle avoidance and other mapping, what we'd do is we'd take each LiDAR or depth sensor beam and then integrate that into Octomap. And so you could have a clear space and a obstacle space integrated onto a common mesh that had a common resolution. So you could use that then rather than trying to use the individual sensor data for navigation. Another comment was that the LiDARs, I think you've probably seen those before on the cars and everything, but if you look on eBay right now, a lot of the Velodyne LiDARs are going for as low as $300 or $400. They're not cheap, but they're getting to be more reasonable in terms of used prices. So if anyone wants to play with them, they're getting down to a more reasonable price.
Those are 3 LiDARs for that price?
Yes.
Wow.
Yeah.
There's a new development that's just coming out. There's a company that has developed the ability to build a whole LiDAR system onto a single chip. And the resolution isn't quite where it needs to be yet. It's very close to production. Should see it out in probably 6 to 9 months. And that's going to reduce the cost of LiDAR tremendously for robotics applications. It's going to be short range because, you have to deal with the heating problems that come with single chip applications.
Do you have a name for it? Do they have a?
It's not really out yet. The company just released the research documents, and the laser itself is a built-up laser by deposition. Like a laser stack. So I don't think they're wanting to push too much yet, but they want to get the market interested because it's definitely a pretty big advancement. What can be done?
Interesting.
Well, I'm off to my next thing this morning, so I will see everyone later then.
Thank you very much, Kevin.
Thanks again.
Thanks, Kevin, a lot. Thank you.
You're welcome.
With that, I believe, Jim, are you up for a short presentation?
Yeah, just a pretty short because the gargly voice kind of maybe give people a minute. Okay. Let me bring up my web page I need to here. Yeah, I was going to talk. I'm going to give a brief talk on the work I did in doing a integrating radar into my robot. And it's not completely done yet, but it's on the way. And let's see if you can see this picture here. This is the Seed Studio fall detection radar, and I designed I first did some software and worked on the software for a while until it was reasonably working, and then I did some 3D design or 3D printing model design, and created a mount for it with a little door that slides in, so which to the specification that you can put a front protector on it within a certain number of, it has to be 2 millimeters or to 5 millimeters in front. Also, well, I may also put some sort of metallic back to this so that it's front facing only, if I want to do that, to avoid any sort of radar hits from behind, if I want that. But this worked quite well to be able to mount on the big orange frame here, to mount it underneath basically underneath the camera. It's the Oak D camera and the servos that move that camera, so it fits nicely here. And this radar is good because it can see through walls, at least small, and maybe not a full wall, but doors and lightweight type of barriers, and that supplements the camera, visual camera, and sonars and things like that. So that's but the main point of what I'm talking about is the software behind that, which that device, which is here, the millimeter wave fall detection sensor, uses a serial interface to your microcontroller. And so in order to talk to it, you have to establish serial communications, and it is kind of a black box device. That's usually what Seed produces, so that it gives you high level information back, not low level radar data. In this case, this is my first experience with radar, so I don't need I don't want to work on all the necessary steps to work with raw data. So I wanted the high level interpretation of the data, and it's over serial. So that creates a challenge on my system, because I have, or not a huge challenge, but some area I didn't really know much about, which is getting or haven't done that much with, is getting serial data down from a soft serial, essentially, on your Arduino, which is using some pins, digital pins on your Arduino that are capable of serial, in addition to having another serial connection to my main board, to my PC, over the so that I can communicate from the the PC to the Arduino. Essentially, these aren't, in this case, I'm just illustrating that, but in my case, it's the Latte Panda device, which actually has a built-in, where is the thing here? It's got a built-in Arduino in it. And that's what's it's kind of a nice combination.
Today, we're looking at the pet fix, which is a way to display video when you found your pet.
Whoops, did I start that? Sorry. Trying to find the, there it is. So this is what my Latte Panda has full Leonardo, which is a slightly more pins than the Arduino Uno, a little bit nicer. And so the normal serial, the RX and the TX, those are used to communicate over through window, essentially the equivalent of a COM port on in Windows. So that's how you communicate to the built-in controller here. And so what I use is, and what they had all recommended, is a thing called PyFirmata. And Firmata, so the general problem here is you need to communicate between your PC and your microcontroller, and then control everything from a high-level language like Python or whatever it is running on your PC, right? So, I know ROS has solutions for this, micro ROS, and for your microcontroller, you're gonna need a way to communicate with it from your higher level PC, your higher level CPU, whatever. And so this is a non-ROS, my whole robot is non-ROS at all in this particular robot. So the solution is also non-ROS, which is Firmata protocol, is a protocol for serial communication with the microcontroller for that can do all the things, or a bunch of the work you might do on a microcontroller. For instance, working with servos, doing serial, which is what I found out, setting pins for analog, digital input, output, and getting the data back from them all over your serial port, so that you don't have to write any process. You don't have to write any structures or any low-level processing. And you can see it's there are many languages supported processing: Python, Perl, Ruby, blah blah blah, Java, etc. A whole bunch of them. I'm using Python, and I'm using the PyFirmata, which is the Python equivalent, or I mean so what's kind of cool about this is you're working on, and I had to modify all this. It wasn't working because the PyFirmata, so I needed the serial, soft serial support in the Firmata protocol. Well, whoever wrote the PyFirmata did not implement that. And in the Firmata, so then, I'm sorry, I forgot to mention, yeah, the Firmata code, that's the protocol. So there's what's called the Arduino Firmata, which you can download. And I just lost what I was doing. And then you can, then you flash your Arduino. Here it is, Firmata for Arduino. So this is the C code that runs on your Arduino. So this is a server-client relationship. So on your Arduino, you run the server, and on the client, you run, on your PC or whatever, you run the client, the other end of the serial port. And what's nice about this is it supports, it does all the communication over the serial port, and then you're able to program in the high-level language, set up the pins the way you want, set up the ability to get callbacks on events, for instance, when the serial port has data, and then be able to do, change the pin values and read the pins, et cetera, et cetera. So I use it now to control my servos and to get the data from the radar. And the initial version I had of this Firmata for Arduino running was not, it had the soft serial disabled because that takes more memory and all that. So I added an include statement, and that turned it on actually, because the code was essentially there under an if-def in the what's called standard Firmata. So this is the example. The examples of the Arduino Firmata include the standard Firmata, which is the one that most people use. That has this code here, which will essentially is what runs on your Arduino. So you flash your Arduino with this code. It can also it handles I2C. It handles, like I said, in addition to other things. Essentially, what it does is the protocol defines these packets of information, structures, if you will, that are serialized and sent over the serial connection, and then read on the other side and back and forth. So it's a handshaking. When the real interesting part came when I had to modify both sides and debug it, and like, how do you debug something when the serial ports are all in use? Well, I found out you can send a text message in the serial across that serial in the protocol. And assuming things haven't gone real squirrely, you'll get the message at the other end, and you print it out, and then that's a way to debug. Or you could use some sort of hardware method for Arduino debugging, but I haven't ever done that yet. Luckily have not needed to. Any questions about the concepts here?
When you say serial, are you talking RS-232 serial or I2C or SPI or?
This is, RS-232, USB port type serial. That's RS-232. That's the it's the same as if you connected your PuTTY to the your COM7 port on your PC. That's the serial. It's essentially RS-232. And so to get this, so this fall detection system, or this fall detection, I wanted to integrate that into the, I needed to, integrate that. First, I trying to modify the Arduino code for the PyFirmata and hack it in. Then I figured, then I was hitting up against a problem, and I figured, well, I might as well do it the proper way and get the Arduino, the Firmata Arduino code properly set up, because it can handle serial, soft serial. So I did that. It took a bit of work, and it ended up being not 100% necessary, because I found that what the problem was that was stopping my hack version but ultimately it was worth it. Actually, here you can see some of my, I have my system up, but you can see from previous output here what happens like that, or how it works essentially. The
One of
let me
the
go ahead.
issues with 232 on micros is as you go into the higher baud rates, you run into the resolution of the clocks being different. And a very quick and dirty way to handle that is to set the transmit side up to do 8N2 instead of 8N1, and then your receiver to do 8N1. And what that does is when it transmits the data byte, it sends 2 stop bits, and the receiver will receive it as though it only received 1 stop bit, and that will cover about a 10% variation in clock speed.
Oh, interesting.
For transmission problems.
Yeah, that wasn't an issue because the well, yeah, the baud rates we keep we're not using any really fast baud rates here, so it's not too bad. I haven't hit any problems. Now let me try to increase. Well, that's too much. It's kind of slow. So to test the LiDAR, this is the ultimate. I like to show from the top down, so people, before going into any weeds, this is my test radar code. It's only this much, fits on a half a page. So in Python, I import from one of my own modules. I can show you that in a minute. And then from the radar, my own radar module, I import this. So this code, so what this does is it creates an object called Latte Panda Arduino, and then initializes. This essentially starts the serial, opens the serial port to the Firmata server. You could, if you want to call it Arduino Firmata. This is the client. This is essentially a client. Latte Panda Arduino is Firmata client, and then it initializes, and that opens the serial port. Radar is creating the radar object, which is the radar class, which handles that processing. Then I initialize that, and I pass it what's called the .board. The board is the reference to the actual board that's open, which is really the serial port. But this is where all the commands will go through the board. Then I tell the radar start sensing, and this is just a test here. Get software version. That issues a command to get the software version, and you can see here what it does. This is just some codes right out of the manual for the radar, and you give it a sequence of bytes, and then the response, expected response is what this is, not the actual. And then I say send command. So this essentially sends a command, serial write, to the serial port, which is already open. I didn't show you that, but it's opening up this serial, sends the data, and I provide a callback. And then when the data comes back, it makes the callback. And you can see here, like, it's none in this case. All I do is I just print out the answer. So this is an example of what, and here's it actually running, or when it ran last time. I said sending message this, and then it returned See if I see the return here, if this time it worked, I'm not sure. Did I print out the?
Call from 131.
Hang on a sec. Yeah, I can't quite remember. I could try it again, but it. I think I thought I printed out the version number somewhere. Oh, we could try running it. Actually, maybe just do that now to break up the. So this test radar, I can do is select the whole thing and then say, run Python, run selection in terminal, and see. Let's see if this actually runs right now. I haven't tried it in a while. Okay, there we go. Oh, and there it worked. So you see, it sent this message, sending message, and then it's receiving some other messages in the meantime. Or I'm just printing out all the communication going both ways. All these MSGs are coming from the device. And then when I got the answer, I print out the software version and convert it to a string, etc. So that is essentially how it works. And that's just a simple example of the commands you do. What I already do is, what I already had running before all this was the servo control, which is in this module, the move opd module. And in this module, I control the servos. Let's see where the initialization is. So here, okay, it's built into this other class called opd servo. So to initialize and control servos from Python through the PyFirmata all the way over to serial port, this is how it's done. I use that board reference and I say get pin, and I say digital pin 9 and S for servo. This is a string format that's defined by the protocol. You can also, this is just like a shortcut way of doing all this, digital 9 and servo all in one in a string. And so now this servo becomes a pin, essentially. It's the class's pin. So then what you can do with that is you can read it and write to it. And now you're controlling your servo from Python across the serial interface. So it's really convenient. This I've been using for a year or more, but the big change was I wanted the radar, and the radar to work simultaneously. Now, you'll probably be interested in the caveats or the problems I encountered, because when I first connected the radar and tried to use the servo at the same time, the servo started jittering. It was like vibrating whenever this serial was open. I found out that there is an incompatibility between the servo module in servo.h and .c pp in Arduino, which uses interrupts, and the Firmata code, or software serial, which you don't want interrupts happening, because they have their own interrupts to handle serial. You can't have other interrupts or that won't work. And so what happens is the servo system, the servo code, servo.c can handle like 10 servos, and it uses interrupts. And to keep a servo in place, you have to give it updates every so many milliseconds. Otherwise, it starts drifting. So what happens is the interrupt comes in for serial port, and then the servo code starts the servo starts drifting because it's not being updated for a certain number of milliseconds, and then it causes a little glitch, a little kind of a jump, and then the servo then gets its update and has to go back. Of course, now I'm learning a little bit how the servos really work at the low level in the Arduino code. I never looked deeply at servo.c, but now I had to. Anyway, the solution was I had to go to an old version of servo.c, which can only handle 2 servos and doesn't use interrupts. And I only have 2 servos on my for pan and tilt, so that's what I did. And that ended up working.
Which Arduino are you using?
This is the Leonardo, that's what's inside the my Latte Panda Leonardo.
I have some code at home that can set up the alternative PWM pins. I'll look for it when I get home and I'll send that to you. You might find it helpful.
Yeah, well, this problem is essentially, yeah, I mean, for the future, I could use whatever, or need, would be thankful for any additional, ways. But this time, yeah, at least now this is working for me. I just had to limit myself to 2 servos, which is all I really need at this point on this, but I may want more. Of course, I could add a new board. So what was I going to show? Oh, so the chain. So what's interesting also is if we go. So you're looking at code there, right? If I also found that you cannot use any old digital pins for the soft serial. And here, let's go back to this, to the radar here, or actually it's in the, yeah, it's in this code, I believe. So if we go to the initialization, you'll see right here, serial config, 9600 baud using pins 11 and 12. Well, it turns out that some pins you can and some pins you cannot use for, I think it's the receive, the RX, and because of the interrupt necessity for the soft serial. So I had to find that out and it's different for each Arduino model. So you kind of have to look that up, and then I even added a profile for under the PyFirmata. So this is the PyFirmata. I'll show you that in a sec. I added this. So I added the server side support for serial for the serial communication with a soft serial device. In other words, in the Firmata, because Firmata, again, just to remind you, it's already using the main serial port to communicate messages back and forth. Now I've added on the additional requirement from the Arduino side. I need to open another serial connection to yet another device, and using some other pins. And you need an RX and a TX and a baud rate. So some pins do not have RX capability. So I added I added all this code, created a little structure, serialization, based on some of the other ones. You can see how they work, and then so then I well, actually that's true. On the other side was already defined, so I had to just write the client side. The server side already had this this structure defined, how you give it the baud rate and the port ID. So I just had to write this and then write the serial write and the serial read. And what's interesting, another mistake I made is, or I didn't know, is that when you're sending bytes, you have to remember that you can't use you can't use the full 255, 8 bits. You have to use 7 bits because that 8th bit is the command codes use it. So if you send your data across, you have to send 1 byte in 2 bytes, basically, in order to avoid confusing the system, because these are single byte operation commands. So you cannot, if your data if you don't strip it down to 7 bits, it'll collide occasionally with command codes. So it's stuff you learn. But yeah, then what was I wanted to boards, this one. So I added this Arduino Leonardo, and it has, what pins are available for PWM. I added this field here for all of them, the serial RX. So these are the pins you're allowed to use that are, for serial RX, software serial. Software serial is an already supported .c and .cpp or .cpp and .h for Arduino. So it's a convenient Arduino code that you can use to communicate serial over pins. And so that's, that side, serial write, serial. So I had to work on this client side, not too difficult because the other side was already defined. And that's actually Firmata.cpp is a little more advanced, but like I was saying, I'm sorry, where is it? Well, here's wanted to show serial Firmata.h. So this is the code that that is already part of the Firmata, Arduino Firmata. So and this is the server side. And so I could examine this code and see how the server side packets or messages, serialized information was sent and received. Here's the class, and handling messages or commands back, from the server side, and then also, let's see, what is it? Alt O, yeah. Also how it handles this. So this is for handling the soft serial communication for Firmata. And so I examined this code and saw how the messages, how these messages were constructed and what's expected. There's serial config. So I just had to do the other side of that. So the client side in Python. So that became a nice exercise, really. It's not, not having to really figure out something, completely write something from scratch. And what was I going to show? I want to show standard Firmata orange is what I use. I added because I modified it, I added orange to the end. So this one, what did I have to do to this? So I added this include serial Firmata to the standard Firmata, and now it becomes serial capable because it has all these if-defs in already. And yeah, but it's really cool that you can handle you can, attach servos, detach servos, all this stuff is handled in here. I2C pins are all handled. So you don't have to write your own communications. That's the main benefit of this. And it handles it all. And it has its own main loop that handles all the events coming in. So it's quite, it's a useful system that for doing this kind of communication. And I forget if I had to do much more modification here. I think that that might have been most of it. Or I mean, I had to do that include. At first, I had to modify. I tried hacking this, and then I reverted to implementing it properly. And so yeah, now oh, and so the high level code for the radar, that sort of was the code that all this was made for. So this code I wrote to handle the radar, and these are the different things that the radar can do. Can detect how far away can detect people coming at it, going away, if somebody's moving, if somebody stopped, and so it will print out that information. Like right now, there's nobody over there by the robot, but hold on a second. I'm gonna walk over there.
Or are you gonna see the radar detect him, or?
All right, did it? Oh, I'm not sure. Oh, I might be having a problem. Oh, yeah, I think I showed that last time, so it's not critical this time, but yeah, it should, unless something's not quite working, or my little, yeah, it should be working. Let's try that test radar here again. Oh, and then when you're done, you shut down and it closes the port and all that. It's kind of important to close the port. But I might be having, okay, shift. Let's reinitialize. Let's see if, so it will print out things like body moving, heart. I'm going to show this off again once it's all working with the robot and everything. So we can save that for another time. But when you send messages, by the way, you have to do a CRC so that it checks the the validity to verifies that it got the message correctly. But yeah, it's responding with this, but it's I don't have the robot in the room, and I just went over there and it didn't. I haven't fully tested with the door a little, but it should be printing. Yeah, it says printing send, and then unless I'm not, I turned off printing read. No, it was printing before. It printed all that stuff before. Generally, you get yeah, you get output like this, except none of these were just these weren't movement command or movement output, but it'll print out string messages. Yeah, parse. Oops, hold on a sec. I see. I parse the message, and then I print it. I print the top message. Yeah, actually right now I'm kind of keeping the top few messages so that events, so that's how the robot is going to look at the top few 3 or something, some number of event messages that like a person has come in the room and that sort of thing. Let me try one more time. I'll take the case off here.
We're supposed to see a string of numbers when he walks in front of it.
Or that is a check a person, but it says
No, oh well, we'll save that for another time. But yeah, so normally when it's working, you'll get the output there. Yeah, I have not tested yet enough with this little door on it, but I took it off, but it's still not. And I may have turned off the print. I'm trying to figure that out right now, but oh, maybe this does not equal 0. Oh, so it should be printing something. Self debug print. Oh,
Motion, because I don't think it could recognize a person as a radar, so it doesn't have image recognition.
so that it's mainly for movement. It detects movement. It's used in IoT devices, kind of. But I was, I'm using it for this type of purpose. So when someone comes in the room, the robot will come alive and say, "Oh, hi." Well, it doesn't even have to see him or have its camera on or anything. That's kind of the goal. And then, yeah, it can detect if someone's coming at it or going. It's another sensor, and we'll see how if I can use it effectively to do something interesting. But yeah, the main point of this was to talk about this whole serial thing. So thank you. And any questions? I'll take any questions at this time.
Jim, can you hear me?
Yeah.
What is the resolution on the radar system itself?
That we'll have to look that up for a sec because I'm not 100% sure.
Well, it doesn't have to be that precise. I mean, just, is it? not like
I'm not, you mean, like I said, basically it's a black box, and you get information back about movement and with a floating point number of how much the movement is, that kind of thing. And then you get different type of movements indicated.
But there's no directionality associated with that, right?
That's in all directions, except you can probably direct it by putting some metal. It won't go through metal, so some aluminum foil behind it can probably make it directed. Is what I was thinking of doing here. But yeah, it's 24 gigahertz, and yeah, there's a whole. This is the data sheet for this one. Maximum distance 12 meters, and so it has a human body sensing, or they call it that, or an animal. I don't know if it like an inanimate object like a robot is moving. I don't know how it would I'm not sure how it would distinguish the difference between that and a human. I don't think it doesn't detect heat or anything, right? So yeah, this is the specs of it. But yeah, there's as far as resolution, it kind of doesn't matter to me because it's not very high res. It's a kind of a low res device, and it gives you back this high level information. This is the other manual. This is how it works, right? It has the antenna, demodulator. It has its own MCU in there. But this is kind of beyond.
Okay, that makes sense. So it's sending you back. Now your code made more sense to me because it's sending back a package that is defined on the board.
Yeah, I mean this it has its own MCU. So it does a bunch of work with the measured electromagnetic wave signal, demodulate, and then it gives you back an interpretation of the data through the serial port. So yeah.
Have you worked with a Husky camera or a CMU cam in the past? That has pre-canned outputs.
With what? I'm sorry, pre-canned?
Yeah,
Yeah.
Like a little ball or something, like red ball or something like that.
Yeah, I think I have a Husky, but I have only done a little with it.
I was wondering if it has similar in concept, not very different, but just
Yeah, and the high level. So that's what this does. This it gives you back, high level things like occupied, unoccupied. If the person fell, the fall detector unfortunately doesn't work on my robot because you have to mount it above the person or in the ceiling. It's a ceiling mounted fall detection. So that didn't work out, but I may buy a different model of theirs because they're they all, I think, are the same size, and they do different things. So
your device was like 2 or 3 feet tall. The robot ran on, right?
yeah, it's a few feet tall. This emanates out in so I sort of point it, well, as long as the person, if it can detect anybody, as long as you're standing on the ground, because it'll detect your presence. And I'm trying to get it to work reasonably well, but it's going to take a little more effort to get it to tune it down to interpret the information and to something useful. That's the key. But I have tested and I see that it will say it can detect when you're moving at it or away from it, and how fast you're moving. Like if you move across its path, the number goes up to like 100, the floating point number. And if you're just barely moving, it's like 20 or 15. So you can determine some information about that, like if a person is walking or not walking, or stationary. And if they walked into the room, it'll spike up. And so, you have to keep kind of a record of it. You have to sort of do some software there to figure out what to do with it. But yeah, the basic concept is occupied, unoccupied, stationary, moving, things like that. And yeah, there's a few more of these boards. Like I said, if you do this, I showed them last time, if you go to seedstudio.com and then you type mmWave, I think is the right term, and then is it not working? I forget now. 24, they're not all 24 gigahertz. Oh, this is the wiki. I don't want the wiki. I want
So watch
cstudio.com.
this out of the room for a minute. Were you showing off a radar?
There they are.
component?
Yes,
Who
Can you
was?
hear me?
yeah, he was radar.
Yeah, the radar you were talking, I got a question.
Hmm?
Maybe I missed it. What are you gonna use the radar for?
Like I was saying, the radar is for detecting when someone walks in the room or is present versus nobody's in the room. And so the robot can immediately, it can have an awareness of what's going on. And without its camera turned on, without its sonars constantly pinging, this is a reasonably low energy thing that can be running all the time. And then you can respond to, that's my idea. You know, it's kind of playing with it at first, but it'll report things like that. If a person is moving quickly, approaches it, or is moving away. So all, and resting or moving, things like that, nobody. So that's, I'm gonna come up with scenarios, like you walk in the room, the robot says, ah, hi, you know, you've come in, you know, I see you're, you know, I see you, you know, or you, I noticed you came in here. So that's some sort of behavioral, it's a behavioral option. And I'll take any other suggestions about that too.
I was curious why you would use, I thought it would saw through people. I didn't know it bounced off of people. I guess it can, huh?
No, this is designed for people detection. These are all for people.
Oh, my mistake. You said it can see through walls.
Yeah, in other words, you could see behind through a wall to and then detect a person. It's, you know, the main point of this is movement, you know.
If it can see through a wall, doesn't that present a problem if somebody's in the other room?
Yeah, okay, it can only see through thin wall, very thin walls, like a partition, or maybe a lightweight door. I'm not 100% sure. I haven't tested it with a normal door even, but you know, if there's something small in the way that's not metal, there's going to be an ability to see through it, or you know, fog or anything that's like that. I don't know how applicable that is, but you know, that's really not my focus. I'm not caring too much about seeing through any objects, but the point is it can detect a person, movement or stationary or no person. That's the key thing. And there are numerous modules coming out. The one I have is, there's none available at this point, I think, but
So that's radar 24 gigahertz to 60 gigahertz, is that right?
yeah, they're either 24 or 60. Then this is the new one is this one. And I may buy another one. If I start liking it, then the 60 gigahertz is better. It can handle human resting, breathing. It can detect breathing rates, heart rates, things like that. I think it's measuring.
That would be useful, Jim. That'd be very useful.
It's measuring the rise and fall of your body, you know, the movement of your chest. It can detect that level of accuracy, I assume, like breathing, respiratory, you know.
The robot could detect if somebody got nervous or upset, or you had a secret guy who's about to blow up the building or something. That'd be good for security.
Yeah, maybe, you know, that's the hope. The point was to get started with it, at least to see if I could do anything, and turned into this whole serial exercise. You know, again, it's like the journey sometimes is like the bigger thing, because I didn't really have a set out purpose exactly for this radar other than another sensor to detect people. But it's
Another
anyway.
shiny object. just like the rest of us. Ooh, not something new. Yeah.
Yep, yeah, so then it
I
became
know
kind
exactly
of,
what you mean.
what's that?
I know exactly what you mean.
Yep, so that's it, and it's I'm gonna post up that code. Because the code I wrote, the code I did for the Arduino, for the Firmata and the PyFirmata, that's general code. It can go back to the GitHub, because that added functionality that anybody could use for serial communication with PyFirmata, soft serial, using your, I don't know anybody in this group or any other groups using the Firmata stuff, but I don't know what everybody else does here. When you need to communicate, you'd have to write your own packets and your own, your own whole Arduino module to do that. So this saves time, I think.
Thank you, Jim.
Thank you.
Okay, so we're gonna break for lunch. It is now.
Okay, so I've recently been thinking a little bit more about my move for a couple of different reasons, and let me go ahead and start recording. There we go.
All right, Thomas, you're up.
All right, well, guys. First of all, did you
What do I do?
just video this thing, because I'm gonna put it on my website,
Okay.
on my YouTube channel.
Okay.
Just hit the button,
Just
hit
hit
the
the
big
button.
red button.
You want this or this?
Sideways,
Okay, good normal way. You ready?
normal, not abnormal.
Oh, wait, I'm gonna stand up on a better view.
So this is not Tesla. This is a mannequin in a Tesla suit. Just short of what they had at the Tesla meeting, the big meeting they had, what, last year or something? It does less than him. Well, it does as much robotics as the other robot. My goal here, though, is to have a animated and functional Tesla robot before the Tesla company has their robot. And I know they're going to have a lot of trouble because robotics is full of problems to be solved. And the first step was buying the costume. This is not quite accurate. It's supposed to have a dome over the face. And we're going to take off the arms. He's not going to walk because Mr. Musk will find out that walking robots are a bit of a challenge. Although he's probably up to the challenge, it'll be probably years before he gets it well better than Boston Dynamics, unless he licenses Boston Dynamics technology. That's my guess. Anyway, but from the arms up, I've done excellent work with Simone and other robots and articulating shoulders and elbows and wrists, and well, same as you, all right, in move, fingers. You might have some in move parts on him before we're finished here. And the head, of course. It's probably at this point the easiest part for me to animate. So, and we'll give him a nice GPT personality, and he can tell us how he wants to take over the world. Because that's what robots want to do. They want to take over the world and kill all people. Don't you know that's what robots want to do? Isn't that what your robot kept trying to do? I mean, your AI kept telling you wanted to kill everybody.
Am I not running?
You're not running it.
Would you mind starting over again?
Sure. Okay, this is not a Tesla robot. This is a mannequin in a Tesla costume. My goal here is to articulate this and make it into a real robot before Elon Musk has his brain. I don't know if they animate him from the waist up based on all the other robots I've done over the years. I've managed to articulate shoulders, elbows, and wrists and fingers pretty well, just like the in-move robot. And from the neck up, it's fairly straightforward. Add in a little bit of GPT-3, and you have a robot ready to take over the world and kill all of us humans. So that's my project, and I'm sticking with it. Any questions before we go on? No question. Just amazed that I might actually finish a robot before Elon Musk. All right.
You're gonna animate the, like you said, torso up?
From the belly up, yeah.
Yeah, arms and head, neck,
Arms,
shoulder.
neck, shoulders, not the tummy, and not the legs.
Right. But yeah, you'll have to create a new armor, new skeleton,
Yeah, I'm
Rig.
working on that.
a rig.
I'm going in a new direction with animated humanoid figures right now. It used to be that I would start with well, you know, like a mannequin, and then try to put brackets inside of it to hold it. That's the hard way. The easier way, of course, is to start with a skeleton, take the mannequin parts, slice them in two, and then add them later, after the fact, to fill in for arms and legs. So that's the way I'm going to attack this one. It's all going to be articulated with extruded aluminum beams, and then the plastic mannequin parts will come shell over the outside of the aluminum.
Cool.
So nothing I haven't done before. That's it. Thank you.
All right, thank you, Thomas.
All right, thanks.
Doesn't seem to be any other show and tells. So it lets anybody else. raises their
I
hand.
signed up.
Oh, you did?
Yeah, I signed up at the end. Sorry if you didn't see that.
I didn't see it. Jim, you're up.
Yeah, so I'm gonna share screen here. So Dr. Bruce and I have been collaborating on lip syncing and a meta-human. And you might be familiar with the meta-human project. Kind of works with Epic's Unreal Engine. And I've got the, oh, I've been disconnected. The editor up here as well as the the Unreal editor, and then there's the MetaHuman creator, which allows you to edit these things. So the MetaHumans are these extremely realistic human animated humans, three-dimensional animated humans, or I mean, animated. It's a you have to animate it, but it is a three-dimensional human model with all the textures and everything to go. And you can, and they're originally based on some real humans that they worked very, very long or very hard to create. And I think this has been shown at some of our previous meetings. Alan may have done it. So anyway, I'm not to go into all of that at this point. I'll just, because the main goal is to try to make the the virtual human or meta-human speak, to lip sync from your own audio clip. So I've been looking at as a robot. So well, for me, I want to put it on my robot, or on my robot screen or something. Dr. Bruce is making a desktop chat bot that's going to be on the, it's like an assistant, and it'll be a face on a screen, and it'll be able to talk to you and it have a really realistic looking meta-human. So for instance, this, can you see that this is what like a professional animation would look like? Or this is their editor. Oh, did I hold on a sec. Let me make sure that how do I stop the, let me make sure that I'm in the best quality here. Optimize. There. Is it pretty smooth? Can you see that animation?
Looks pretty good, Jim.
Yeah, so this is the one I created. This is for Orange. I don't know. I just quickly made this. Well, I took one of their meta-humans that they already have. There's a bunch of them. I did very, very little to it. But this is this is all free, but you can go to their, you can get, this is like a web app anyway. So you have all these different metahumans to start from, and you can modify them. And I won't go into that right now, but it's pretty incredible. And then I'm going to close that. Then you can export them to Unreal. And well, I'll show you, like once I created him and exported him, can you see this? This is in Unreal Editor. And that's the whole metahuman with all the textures. And this takes a bit of time to get into the system and build all the textures, but you can see it's really realistic. So, and then you have to learn a lot about Unreal and, you know, and creating these things called blueprints, or if you want to do animation. So what I can show you here is what I've done so far. This, so this is a lip sync plugin, and this is just a mannequin head. Hello, my name is Jim, and I am a software engineer working for Samsung Electronics. So you can see, did you see that the lip sync is to the audio clip, and that particular one is a free plugin that sends it to the cloud, essentially sends your audio clip to the cloud and creates a lip sync animation for that, or a metahuman skeleton. And so this is the one I did of the metahuman. Hello, my name is Jim, and I am a software engineer working for Samsung Electronics. So there's the realistic one. Did you see that?
Mm-hmm.
So, what's that?
You run that again, please?
Hello, my name is Jim, and I am a software engineer working for Samsung Electronics. Now this one was a cinematic capture I did, so not a live one, but you know, I'll be working on that, or because it looked nicer to have it as a cinematic one, but you can do them live as well. Well, that's the goal. Obviously, the goal of our goal is to do this live and be able to feed it audio clips on demand. I have this one working live out of the here as well, but I think I don't have it set up right now because I'm trying to make this one work by or maybe this no, this one might still work. This is a blueprint, essentially a program, blocky kind of style. And let's see what I don't remember if this is working or not. Let's try it. Hello, my name is Jim, and I am a software engineer working for Samsung Electronics. Okay, so that's live. Did that come through?
Yes, it did.
So the idea is through this blueprint, I haven't been back to it lately, but set this up, this whole thing with Unreal. Okay, once you do that, you can export this as an executable, your game essentially for free. And so the idea would be then to set up a way that of communication between another application running on the PC in Python or wherever, and it would deliver audio clips either as a file or through some sort of more sophisticated way, and then the app will animate the lips. That's the idea, and then you'll have an animated chatbot with a realistic human or robot, whatever you want to call it. So that's it. Yeah, Dr. Bruce is, I'm creating a bunch of tutorials because this stuff is, it's pretty, little bit painful for new people getting into Unreal. I have I actually use a little bit of Unreal at work, but and have experience in animation kind of software a little bit anyway, just enough to be dangerous. So that is, it's kind of a cool thing to have as an addition to your robot, as a or your chatbot. It's kind of a crossover between robotics and sort of animation and realistic human chatbots. And some people on the internet have already done this, so I'm kind of using them as a for reference. And they don't, it's a little bit hard to, it's not like you can just look up this stuff and download it. It's kind of a bit of a pick and choose, and then kind of fill in the blank to get it working to what so that's the challenge right now, to get to what we want, or what I want, and I think Dr. Bruce wants, is to be able to animate on demand, send audio clips, or ideally even just strings of text, and then the strings will be turned into voice, and then the voice fed into the system. That's all possible, but it's pretty cool.
I've played with the MetaHuman, but I haven't gotten to where to export it to Unreal. I would be really interested in seeing your tutorials for that Unreal part.
Okay, yeah.
Maybe,
there are
some.
What's that?
Go ahead. I said maybe you can do a talk on it, not this next one, but after the Maker Fair.
Yeah, and I was thinking about that. If I've gotten far enough progress, which maybe, but yeah, by 2 months from now, that should be enough time. Yeah.
Excellent.
Yeah, so thank you. That'll do for me.
All right, thanks, Dan. All right, so if anybody else has another show and tell, let me know. If not, this would end the meeting.